So in this video, I'm going to talk about the infinitely repeated games. So these are the games that are played on a repeated basis, and there is no, end in sight. So they are played for, on an infinite horizon. So to better understand the infinitely repeated games, let's go back to one of the games that we considered previously, and it's called the Prisoner's Dilemma game. So let me draw the normal form version of the Prisoner's Dilemma game. So let's say there are two players, 1 and 2, and they have two strategies to play the game: cooperate or defect. Cooperate or defect. So let's say the payoffs are, if they both cooperate, they get $2 in each time period. Think of it as profit, maybe $2 million each year or something like that. These are two firms, let's say. And if they both defect, then the profits are $1 million to them, both of them. And if one firm defects, other firm cooperates, then the profits are 3 and 0. And let's say here 0 and 3. So this is your classic Prisoner's Dilemma game. So if this game is played only once, right? So it's a one-shot game, simultaneous move, one-shot game, then the Nash equilibrium of this game, if you remember, is going to be where both players defect, right? So if player 2 chooses to cooperate, and best response for player 1 is to defect. And if player 2 chooses to defect, the best response for player 1 is to defect. And similarly, if player 1 chooses to cooperate, then player 2's best response is to defect. And if player 1 chooses to defect, then player 2's best response is to defect. So clearly, this is your Nash equilibrium of the game. Now, in this game, as you can see, there is a better outcome here, right? This one, where if they cooperate with each other, then they're going to get $2 million in profit. But since they are taking action in their best interest and they're rational and they cannot coordinate with each other, right? They can't talk to each other. It's a one-shot game. Then the Nash equilibrium, will prevail. And this is, not the better outcome for them collectively, right? They could do better by playing cooperate. So the question is, what would make them cooperate? Okay. So to understand it, let's suppose this game, the exact same game that we are considering here, is going to be played on a repeated basis till infinity. So think of this, that these two firms, they interact each year, and these are the payoffs, right? Every year they get the same payoffs in dollar terms, right? And they're repeating this game. So what would happen in that kind of scenario? So there are two possibilities here. They can, they can basically keep on cooperating. So they agree to cooperate, right? Every year, and then they can reap the benefits of $2 million, right? Every year. Or there, one firm can defect. They can deviate from the agreed upon, cooperative, move, and in that case they can make more. As you can see here, if player 1 defects, it makes $3 million, and player 2, if it continues to, if player 2 continues to cooperate, right? So there's an incentive to deviate, as you can see, right? So let's look at the payoff, right? The string. So if they both cooperate, so let's look at first the payoff of player 1. This game is symmetric, so we don't have to consider the payoff for player 2 because it's going to be exact same thing, right? So it's a symmetric game. So let's just consider player 1 or firm 1. So if firm one cooperates, then in time period one, right? Let's say first year, firm one is going to make $2 million in profit. And in the next year, if they both cooperate, again, they're going to make $2 million, right? And so on. But keep in mind that dollar value earned tomorrow is not the same as dollar value earned today. So we need to discount the future income or future cash stream back to the present by using a discount factor. So let's say delta, which belongs to 0 and 1, is the discount factor. Okay, so we're going to use delta to discount the future payoffs to bring it to the present, right? So discount factor. Okay, so delta belongs to 0 and 1. It's a number between 0 and 1. So in the second time period, firm one is going to earn $2 million, but then you need to discount it with this delta, right? And in the third year, again, if they cooperate, firm one is going to make $2 million, but then it needs to be discounted by delta square, and so on. So delta cube and delta raised to the power 4. And it keeps on going till infinity, right? We don't know when the game is going to end. So this is the payoff stream we are looking at in this game, if they cooperate, both players, right? So the question is, what does it add up to, right? You're going towards infinity, so how much is going to add up? $2 million each, right? So we can sum it up till infinity. So let me go to the next page here. So let's look at the payoff for player one. Okay. So payoff for player one is $2 million in the first year, and then 2 delta plus 2 delta square, and so on. So here we can factor out 2 because that's common in every term here. So we get 1 plus delta plus delta squared plus delta cube. That's right. So the terms we have inside the bracket, if you notice, it follows a geometric progression. A geometric progression. So it's a particular type of series it follows. So we can sum it up till infinity by using a simple formula. So the formula to sum, the geometric progression till infinity is sigma. So you're looking at this Sn. So we don't know what n is till infinity. So n starts from time period 1 all the way to infinity. And this is the series you are summing up. So the formula is A over 1 minus R, where A is the first term in the series. And R is the common ratio. So let's focus inside the bracket here. First term of the series is 1, right? Inside the bracket. So A is 1. And 1 divided by 1 minus R. R is the common ratio, and common ratio is delta. So if you sum up the terms inside the bracket here, right, this one, that's equal to 1 over 1 minus delta. And then you multiply it by 2 because that's outside. So basically the payoff is $2 million over 1 minus delta. So if you sum all these, payoffs till infinity, so $2 million plus $2 million times delta plus 2 million times delta square and so on till infinity, this adds up to $2 million over 1 minus delta. It depends on what the delta is. Delta is a number between 0 and 1, right? All right, so that's the payoff from cooperative to both players, because payoffs are symmetric here. So we don't have to do for this exercise for player 2. But if the payoffs are not symmetric, then you would be doing it for player 2 as well, right? All right. Next, let's see what happens if the players defect, right? They don't cooperate, right? And there is an incentive, as you saw in the game, to defect. So we'll assume that the players, since they have made this agreement to cooperate in every time period, and if they see that one player hasn't cooperated as agreed upon, then they will be punished. And the punishment is that moving forward, they are going to play the Nash equilibrium in every time period in the future. So what are the payoffs then? So we call this Grimm trigger strategy, or just trigger strategy. Grimm trigger strategy. Or plainly you can say it's trigger strategy. So basically trigger strategy or Grimm trigger strategy is that when players deviate from the cooperative agreement they made, right? They were playing cooperate, and then one party defected, then the other party is going to punish by playing Nash equilibrium forever. Okay, so that's your Grimm trigger strategy. So let's see what happens to the payoffs then. So we know, if you go back to the game, if let's say player 1 defects in just time period 1, okay, they agreed, and right in the first year, let's say player 1 defects. So in that case, player 1 is going to earn $3 million. And let's say player 2 does not defect, continues to cooperate in first time period, then is going to make a loss of 0. So payoff to player 1 in the first time period is $3 million, and to player 2 is 0. But then in second time period, in second year, player 2 will know that player 1 did not cooperate, and therefore player 2 will play Nash equilibrium strategies and force player 1 to play Nash. Because it has defected, it will continue to play that, and in that case, it will make $1 million. So both firms will make $1 million by playing Nash equilibrium strategies moving forward, right? So let's look at this payoff stream here. So payoff for player 1, let's write it down. From strategy D, right, from defecting. So we know player 1, if chooses to defect, then makes $3 million. So if it deviates, it makes $3 million, and then afterwards, $1 million. 1 times delta plus 1 times delta squared plus 1 times delta cube, and so on till infinity. Because the other player will play Nash equilibrium strategy, and that will result in $1 million to both of them. All right, so now we need to add this up till infinity. So first time period is $3 million, that is not discounted. But after that, we have 1 delta plus 1 delta squared and so on. So if you follow the previous calculation we did, this will sum up to, so delta is the first term in the series, and then 1 minus delta, right? The common ratio is delta. So this is the payoff. $3 million plus delta over 1 minus delta will be the payoff moving forward by playing this, strategy, defect or deviate. All right, so then we can compare the two payoffs here. So the payoff from cooperation was $2 million over 1 minus delta, right? And the payoff from defection, right, is 3 plus delta over 1 minus delta. So as long as payoff from cooperation is greater than the payoff from defection, the players will cooperate. They have no incentive then, right, to defect because the payoff would not be greater. So if this condition is satisfied, then the players will cooperate forever, right? So what is the value of delta that will make this possible? So we can solve for it here. So 2 over 1 minus delta is greater than, so I'll write 3 times, so I'm just simplifying it. So 3 times 1 minus delta, so 3 minus 3 delta plus delta, and over 1 minus delta. So deltas will cancel out here. Let's use a different color. So then we are left with 2 on the left-hand side. So let's bring it here, 2, and then 3 comes this side. So minus 3 is greater than minus 3 delta plus delta, which is minus 2 delta. So 2 minus 3 is -1. -1 is greater than -2 delta, or delta is greater than 1/2. So if the discount factor is greater than 1/2, then the players would cooperate. There is an incentive for both players to cooperate forever in this game, and they can accomplish that better outcome in the prisoner's dilemma game. But if delta happens to be less than 1/2, then they have an incentive to defect or deviate from the cooperative outcome, and the payoffs would be greater in that case. So this is how we can sustain cooperation in a prisoner's dilemma game. And this is how you solve for an infinitely repeated game.